Hi, I'm Pete Warden, and welcome to a screen share covering some material from the TinyML book that I and my co-author Dan put together on running ML on really tiny computers. So this screen share is going to assume that you have a copy of the TinyML book, either a paper copy, or I actually prefer the ebook PDF version. And that's what I'm going to be showing you because it's really easy to click on links. And what we're going to be talking about is running machine learning on devices that are able to run on really tiny amounts of power and are super cheap. Things like microcontrollers or DSPs or embedded devices. And for a lot of the chapters of this book, you're actually going to need a real device to play with. I'm going to be focusing on chapter 4 of the book, which is the first chapter about how to train a model. So for this, you don't need a small device yet. You only need a web browser and some sort of desktop machine that's suitable for running the web applications that you need to just train a model. So in later chapters, you'll need something like this SparkFun Edge board, or we have an Arduino BLE, sorry, let me just check, the Nano 33 Sense BLE board, and there's a whole line of these Arduino Sense boards too, which are all pretty compatible. But happily, for this very first chapter, you only need a web browser. We're only going to be doing training using Google's Colab tool, which you can run in the web browser, so you don't actually need any kind of device yet. So I'm going to be talking you through exactly what you have to do to train a model. But to start with, I want to explain a bit of background to this chapter. So chapter 4 is the first chapter where we're actually asking you to do some practical examples. And this was a bit of a challenge because we're aiming the book at anyone who's really able to run a command in a terminal. We're not expecting that you have any background in machine learning or any background in embedded programming. So that meant that it was quite a challenge to figure out, okay, what's the simplest way to explain some of the fundamental things that you need to do in order to get machine learning running on one of these tiny devices. Typically with machine learning, if you were doing something that was aimed at a desktop machine, you would use an example like MNIST, which is a way of putting together a model that's able to recognize very low resolution handwritten digits. But that's not very useful in an embedded setting because these embedded devices that we're working with, they don't have displays. And they don't have cameras generally, though we will be talking in some later chapters about some more sophisticated setups which do have cameras included. So how are we going to demonstrate this? I mean, the other thing that we often do in the cloud or in the desktop side when we're starting on a new technology, starting to teach a new technology, is actually put together what's called a Hello World program. And what this is it's the simplest possible program in a language which will print out Hello World to the output of the terminal when you run it. But again, we can't actually simply see a terminal on one of these devices. We will talk about how you can get sort of debug logging output, but compared to desktop machines where the terminal is the simplest thing to see, it's not straightforward to get terminal output on this, and also that wouldn't involve any machine learning. So honestly, I was a bit stuck on how to get started on this, but my co-author Dan had a really good idea. He actually thought about the traditional equivalent of Hello World on embedded devices, which is to have an LED blink. You'll often see this program called Blinky or something like that. And so in order to tell that a program is running at all and to run the simplest possible program, you just set up something which starts an LED blinking, and then you know you've successfully flashed it to the machine. So Dan's thought was, well, what if we could create a machine learning model whose output controlled the LED and made it very obvious whether or not the LED was working. And what he came up with was this idea of, hey, can we train a machine learning model to learn what a sine wave looks like? So you put in an input that represents the x-axis and increases over time, and then you actually get the LED to fade and rise in brightness on a sine model. So that's what we are now calling the Hello World equivalent for TinyML. And this chapter is going to be about how you actually take that idea and turn it into a model that's small enough to fit on an embedded device, but that will learn how to output that sine wave so you can actually control an LED. And we aren't going to get as far as running it on a device in this chapter because there's enough work for one chapter just in training it. So that's what we're going to be diving into. I'll get you started on that in just a second. So I've just explained why we're doing what we're doing. Now let's dive into actually messing around with some of the code. So if you have the book in front of you, go to chapter 4, and if you have it in a PDF, that makes it really easy to just click on the links. If you don't have the PDF handy, I'll actually make sure I put the important links into the description of the video. So there's a bit of an introduction that's describing what we're actually going to do in this chapter. And as I mentioned, we're trying to build a model that's able to learn how to generate a sine wave. So as it says here, our goal is to train a model that can take a value x and predict its sine y. Now, as it mentions, this isn't a particularly useful machine learning model because you have lots of libraries. It's easy to calculate sine. You just use a math library. But the reason we're doing this is it shows how you can actually take a machine learning model to learn some kind of function, and the same principles apply to all sorts of more complex functions that you can't actually analytically calculate. So just forget the fact that sine is actually really easy to calculate analytically, and just see this as a teaching example for how you can actually create a machine learning model that will learn much more complex functions in the future. So we're going to be diving in to using Python, and because Python is pretty tricky sometimes to install on machines, on desktop machines, and there are lots of different versions and lots of different packages. What we're going to be doing is using Python inside a web browser window. So it's using a technology called Jupyter, I guess, and this allows you to run Python online together with a tool called Colaboratory, or Colab for short, that's made by Google. So this makes it really easy to run Python using Google's machines online without having to do any setup on your side. And we're going to be using TensorFlow through the Keras API. I work on TensorFlow, so that was kind of a natural choice for me. But it's also because TensorFlow Lite for microcontrollers, which is the framework that the book uses, is part of TensorFlow and integrates very, very tightly with TensorFlow. So the first thing you need to do is load the notebook. So you can see it's this link here, which is oreil.ly/A 78L, and I hope that's a 0, or it might be an O. But anyway, the link will be in the description and in your book. So the first thing you do is load the notebook by clicking on it, and that will load it in a new tab. And my mistake, I should have mentioned this is a release version of the book, and we just moved TensorFlow Lite Micro from the experimental folder into its own folder. So you can now find it at the link without experimental in the middle. So if we load up this notebook, you can see there's a link to run this in Google Colab. And I'm just going to make sure we have the PDF here too, so we can keep following this along. And this is why I like doing live screencasts. You can see me getting confused and getting lost, and hopefully you won't feel so bad if you if you find yourself in the same position. So I'm going to click on this link to run it in Google Colab, and I'm going to hold down Command so it opens in a new window, hopefully, or not. But anyway, we have now got to the point where we have that Python notebook running in Google Colab. Now I'm going to go back to the book and actually walk through what we're going to do as we're working through this notebook. So one of the first things we want to do is this notebook comes with expected outputs often. So what we want to do as a thing to get started is actually clear those expected outputs so we can see just the outputs we need. So I'm going to go to clear all outputs, and that will actually get rid of any pre-existing outputs in there. So the first thing we need to do in the actual code is import these dependencies. As I mentioned, we're installing TensorFlow. We're also installing NumPy, which is a useful math library, and we're installing a library that lets us plot graphs so we can actually inspect what's happening in the data that we're using. And to run this, you can press the run button here, or you can just press Control Enter or Command Enter to run it. And I like doing the Command Enter. So you'll see that it's saying, hey, I'm running. It's, in this case, it's installing a version of TensorFlow 2.0 because at this point 2.0 was not already available, but it's using pip to install that. It's getting rid of TensorFlow 1.15, and then we'll install 2.0 over the top of it. So if we just wait for a few minutes, I've got my cup of tea here, just a sip while I'm waiting for this to finish, and hopefully this won't only take a few more seconds. If not, I may end up speeding up this part of the video. Okay, it actually looks like it is completed. And you can tell it's completed because the icon here has changed from the spinning one to the just plain play one. So in the book chapter, we talk about how you need data to teach a machine learning model. And since we can calculate sine, you might think, oh, well, we can just provide perfect data. The trouble with doing that is partly it just wouldn't be as much fun, and it also doesn't reflect the kind of real-world data that we expect to see. Almost always when we're collecting data, we aren't getting super clean generated data like this that reflects the true underlying function. We've got all sorts of measurement and other errors that creep in. So we get data that approximates the true underlying function, and we rely on our machine learning to actually figure out how to understand what the real function underlying the noise actually is. So we add some randomness to simulate this. And another important thing about machine learning is we actually need to separate the data into different parts. At random, we need to use a whole bunch of the data for training, but we also need to be able to tell how well the training is doing on data that the model has not been trained on. The trouble with if you were just using the whole data set for training is that it could memorize everything in that training data set, and then it's very hard to tell when you're testing if it's really learned the function that's underlying the data, if it's generalized, or if it's just memorized kind of the arbitrary data that you've been giving it. So having a validation data set is really useful because as you're training, you can compare how it runs on data that it's seen before, the accuracy it gives when running on training data, versus how it runs on data that hasn't been fed into the training process. So that's validation data, and that's why you have the validation data set. Now, we also traditionally actually have a third data set, which we only use for evaluation after we've trained. And this testing data set is really important because if you're doing a lot of training, you might actually end up making decisions that favor the validation data set, even though it's not being fed into the training. You could be tweaking hyperparameters or something like that, which just happen to improve the results on the validation data set, So you're doing kind of almost human-led learning on the validation data set in that case, and keeping aside this kind of precious, very seldom looked at test data set helps keep us all honest, because we won't have been tweaking anything around the architecture or any incidental stuff that might help the validation data set. So we split up our data set with 60% of it used for training, and then 20% for validation, which is evaluation during training, and then we keep an extra 20% of it aside for the final very infrequent testing, just as a check that we really are learning something, learning to predict well rather than just memorizing the data. So you can see the code here. I'm actually going to run this in the notebook. We're saying we want 1,000 samples. We're setting a random seed. And in this case, this first one is just going to show us the super clean set of data. So if I press Control Enter, you'll see that super clean sine wave that comes from having kind of 1,000 randomly generated samples. As we mentioned, what we actually want is some noise in there so that it's a more realistic data set and it's a little more challenging for the model to learn. So you can see now we have that kind of very distinctive fuzziness around the values. And finally, we split the data up into the 3 training, validation, and testing sets. So I'm going to Control Enter on this. And you can see that you've kind of randomly got this mixture of the 3 different sets. Okay, so we've now got some input data that's split up in the right way. What are we going to do with it? We're going to use Keras to build a model. And we're going to try and make this model as simple as possible for the first instance. And luckily, that's pretty straightforward with Keras. Keras has a really nice API. You start off by saying, hey, I want to have a sequential model that's a simple model architecture with layers in a series. You add a layer which is going to try and recognize the patterns, and then you add a final layer which takes the outputs from the first layer and then uses that to make predictions to try and come out with that y value given an x input. And then you do some magic to compile that, and then we'll get a view of what's happening in the model. So I'm going to jump over to the notebook. If I just select that again, and again I like Control Enter, you can always hit the, or Command Enter, you can always hit the play button instead, and you'll see the play button very quickly just runs through that model creation. And in this case we don't actually have the model1.summary that's included in the book, but you can always add that if you want. It just prints out a bit of information. So let me actually go down now to the model training, and this is a nice API because it covers all of the complexity of what's happening during training. You tell it that you want 1,000 epochs, and you have a batch size of 16. And in the chapter we talk about how you pick batch sizes in order to get the best outputs. So you have some choices here. Let me just go down to this. You can see that we choose batch size 16, and we're going to train for about 1,000 epochs. And if you want more information on what these arguments here, you can see the information in the book here. So let's go to this and let's see if we can actually start this training. Now this may take a little while because we're going through 1,000 epochs. Each epoch, as the notebook mentions, is running through the data set once. So the entire, I think, 600 points that we have, because we took 60% of a 1,000 entry data set. And it will do that 1,000 times. So let's get that running. You can see it's printing a whole bunch of information, and based on the speed, it should take hopefully less than a minute looking at this. So time for another quick sip of tea. And you can see some metrics here, the loss, the mean average error, and the loss and the mean average error on the validation set. And if you remember, that's the 20% of the data set that we reserved for evaluation during training. And what's interesting is kind of these two values are telling you how accurate things are actually getting. So let's have a look at some of those data points in a bit more detail. So again, Command or Control Enter, and you can see that, as you might expect for a machine learning model, the training loss and the validation loss drop pretty fast, but it's kind of hard to tell what's actually happening after that initial kind of hockey stick drop there. So let's actually skip those first 50 epochs where things are changing very rapidly and just look at the rest of the data. And what you can see is that you have a decent loss until a decent reduction in the loss numbers until around 600 epochs. So that's about the furthest that you really want to bother training. You're not getting much benefit after 600 epochs. But the lowest loss value is about a 15% error. And to understand that a bit more, we're going to plot the mean average, or mean absolute, error. When I said mean average before, I meant mean absolute. So let's have a look at what this is showing us. And you can see that the training data, which is in green, is almost always better than the validation data. And that is a bad sign, because it means that the machine learning model has learned to put too much weight on the training data that it's learned, and it doesn't generalize well to other data that it hasn't been trained on, which is known as overfitting. And the mean absolute error is pretty bad. It means that a lot of the predictions are 30% off from the actual sine wave function. So this is pretty bad. So let's see if we can look at this in another way by plotting some predicted values, and it's pretty obvious here that the red data, which is the prediction, is really not learning much of a sine wave function at all. It's a very poor approximation. It's a sign here that the straight lines and the rigidity here are a sign that the model just didn't have the capacity to actually learn this function. So to help fix that, we can add another layer to our model. And you can see here that we're creating model 2. And just like before, this has an initial fully connected layer, as it's known, a sort of a dense layer that has a ReLU activation output, and it takes in the X value that we're feeding in, but we actually add a new second layer as well. And this second layer is the same shape as the first layer with 16 neurons, but each neuron takes in 16 inputs rather than the original first layer, which takes in only the one input for each of the 16 neurons. And then we have the final layer, which takes the output of that second layer and makes a prediction from it. And just like before, we then set up the model to be optimized using a fairly standard optimizer and to output some of our metrics. So I'm going to run this. That's pretty fast because it's just setting up the architecture. And then since we figured out before that we really only needed 600 epochs, we've changed epochs to be 600 here, and then I'm going to run this model. And this takes a little bit longer to train than the original model because it has a larger architecture. There are more mathematical operations involved in training this, but it's still comparatively fast to train. I might be able to get another sip of tea since I have a little bit left, but it's almost done. So let's see how this is doing. It's very, very close. And it's completed. And the first good news is that the loss function is very small and the mean absolute error on the training is only about 0.09, so about 9% rather than 30%. And it's around the same for the validation set as the training set, which is another good sign. So let's print out those same graphs that we actually used before and see what we can make of them. This first graph isn't that helpful because it hides a lot of the really interesting stuff in the last 100 layers. But if we leave the first 100 layers out and only look at 100 to 600, you can see that we actually have a pretty good looking training slope, and the loss looks pretty good, and the mean absolute error also looks really good. And our network seems to be performing well, so let's check that out by actually plotting it. So here we are comparing predictions against the absolute values. And if you remember before, the red line was very poor. You can actually now see that the red line looks much, much better than we saw before. If we go up here, you can see that the once I get past all of these training sections, you can see that this was actually the original predictions without the extra layer. So these predictions that we now have are much better. I can make back here. Yeah, you can see the red line looks much more like a real sine wave. You can see it's still not exactly right. It's not exactly analytical, but it's done a pretty good job of learning this. And as we say here, this looks good enough for what we need to do. We want something that's going to smoothly blink an LED, smoothly have an LED come on and off, and this looks pretty good. So that's it. If you made it this far, congratulations. You've trained a machine learning model using Keras and TensorFlow that does what we were setting out to do. Now there's some housekeeping in that so far we've been working in Python, and specifically in desktop Python. In order to have a model that runs well on embedded systems, we need to convert that down to TensorFlow Lite, which is a part of the TensorFlow family that runs on mobile devices and embedded devices. Luckily, that's all part of the same TensorFlow suite that we've already installed. So we can use the TF Lite converter to run the conversion and actually write it out onto disk. So I'm going to run this cell, and it will take a few seconds, and now it's written it out to disk. Now if we want to actually try that, we're going to try loading that model from disk and using the TensorFlow Lite interpreter to run it and then plot the results. So as you'd expect, we see the actual predictions are pretty close, pretty good, and especially what we've actually done here is quantize the model, so that what that means is we're using 8-bit integers instead of floating point values to store things like the weights, but it's not actually affecting our overall accuracy. But as we see here, the quantized size is a bit smaller. The interesting thing here is that the weights are so small as part of the overall file size that converting the weights down doesn't make that much of a difference, but for larger models it really makes much more of an impact. And now we actually need to convert the file that we have on a file system into a .cc file. And the reason that we're doing this is because most embedded systems don't have file systems. So if we want to run on an embedded device, the easiest way is to turn the model, turn the file that's on disk into a data array, a C data array that can actually just be linked in, and then we can use that as normal. So I'm going to run that conversion process. Give it a second just to install the XXD, and then you can see that it's actually output a C data file, and you can imagine how you will just add this into your project. And incidentally, we do have some more advanced utility functions now which automate some of this from Python, and I'll add links to that new API in the video description. But for now, this should be enough to get you started. And congratulations! That's it. You've got through this first example chapter. You have a model that's now ready to run in TensorFlow Lite on one of these embedded systems. And in the next chapter in Screenshare, we'll actually walk you through how you can take that model and run it on one of these devices. So thanks so much for listening. I'll look forward to hearing how you get on, and I hope you tune in for the next episode.